This is section 3.2, part C, calculating the equation of the least squares line. Another reason for studying least squares line regression is that the problem of finding its equation has a simple answer. We can give the equation of the least squares regression line in terms of the mean and standard deviations of the two variables and their correlation. We have data on an explanatory variable x and a response variable y for n individuals. For the data, calculate the means x bar and y bar and the standard deviations s sub x and s sub y of the two variables and their correlation r. The least squares regression line is the line of the form y hat is equal to a plus bx with a slope b that is equal to r times the standard deviation of the y variables over the standard deviation of the x's, and the y-intercept a is equal to the mean of the y's minus the slope times the mean of the x's. A least squares regression line will always pass through a point that contains the mean of the x and the mean of the y as x and y coordinates. The formula sheet on your AP exam uses a different notation. It's going to say b sub 1 is equal to r times s sub y over s sub x, and b sub 0 is equal to y bar minus b sub 1 times x bar. This is because their least squares regression line uses b sub 0 and b sub 1 instead of a and b. Just remember, whichever one is attached to your x is your slope. So again, to find the slope, which is our b value, we're going to do r times s sub y over s sub x. This is a close connection between the correlation and the slope of the least squares line, because if the correlation is negative, the slope is going down. If the slope is positive, that means the r value is also positive. The slope equation says that a change of one standard deviation in x corresponds into r times the standard deviation in y. When the variables are perfectly correlated, that means the r value is 1 or negative 1, depending if it's positive or negatively associated, the change in the predicted response, y hat, is the same in standard deviation units as the change in x. Otherwise, because r value can be anywhere between negative 1 and positive 1, the change of y hat is less than the change of x. As the correlation grows less strong, the prediction of y hat is less in the response to the change of x. When doing calculations for the least squares regression line, don't round until the end of the problem. Use as many decimal places as your calculator stores to get accurate values for the slope and for the y-intercept. So we have data from that non-exercise activity change and the fat gain, and we know from these data values that the mean and the standard deviation of the 16 changes in the non-exercise activity has x bar equals 324.8 calories, and the standard deviation is 257.66 calories. Now for the 16 fat gains, the mean standard deviation is y bar is equal to 2.388 kilograms, and s sub y is 1.1389 kilograms. And we know the correlation between these two variables is r is equal to negative 0.7786. We need to find the equation of the least squares regression line to predict fat gain from the NEA change. So if we look at this, the first thing we're going to have to do is we're going to have to find our slope. Now remember, the slope formula is r times s sub y over s sub x. So we know our r value is negative 0.7786, and we're going to multiply that by the standard deviation of y over the standard deviation of x. And when we do that, we're going to get a b value, or a slope, of negative 0.00344 kilograms per calorie. Now the least squares regression line of fat gain y on NEA change x has a y-intercept equation that says a is equal to y y bar minus b times x bar. Now we know our y bar, we know the mean of our y values is 2.388, minus, we just found our slope is negative 0.00344, and we're going to multiply that by the mean of the x variable, and that's going to give us our y-intercept of 3.505 kilograms. So now we know our b value, and we know our a value, so we can plug it into our equation for the least squares regression line. Remember, the least squares regression line has the equation of y hat is equal to a plus b times x. So our equation is going to be y hat is equal to 3.505 minus 0.00344x. Now, what change in fat gain does the regression line predict for every additional 257.66 calories? So, in the NEA increase of 257.66 is one standard deviation, okay? We know that that's just one standard deviation in the x's. And we know that one times the standard deviation of x is equal to r times the standard deviation of y. Now we know our r value is negative 0.7786, and we know our standard deviation for y is equal to 1.1389. So if we multiply those two together, we're going to get negative 0.89 kilograms. So our regression line predicts a decrease of 0.89 kilograms in fat gained for every additional one standard deviation, which is 257.66 calories of NEA change. What happens if we standardize both variables? Standardizing a variable converts its mean to 0 and its standard deviation to 1. Doing this to both x and y will transform the point that is the mean of the x's and the mean of the y's to 0, 0. So the least squares line for the standardized value will pass through the origin or pass through 0, 0. The slope of this new line, b equals r times s of y over s of x. Since we have standardized this, we know that s of x and s of y are both 1, so the new slope of this line would just be your correlation r. One of the first principles of data analysis is to look for an overall pattern and for striking departures from the pattern. A regression line describes the overall pattern of a linear relationship between an explanatory variable and a response variable. We see departures from this pattern by looking at the residuals. So let's go back and look at this fat gain and non-exercise activity study again that involved 16 young people who volunteered to overeat for 8 weeks. Those whose NEA rose substantially gained less fat than others. Now we know that the least squares regression line was that the fat gain prediction is equal to 3.505 minus 0.00344 times the NEA change. One subject's NEA rose by 135 calories, and this subject gained 2.7 kilograms. What is their residual? So to find this, we first have to find their predicted. So we would do 3.505 minus 0.00344 times 135. And that's going to give us that our fat gain prediction based on our equation is 3.04 kilograms. Now remember, the residual is equal to the observed y minus the predicted y, or y minus y hat. So our observed, we know that they gained 2.7 kilograms. We predicted that they would gain 3.04 kilograms. So that's going to give us a residual of 0.34 kilograms. This residual is negative because the data point actually falls below our line of prediction. Because the residual shows how far the data falls from our regression line, examining the residuals helps assess how well the line describes the data. Although residuals can be calculated from any model that is fitted to the data, the residuals from the least squares line has a special property. The mean of the least squares residuals is always 0. So we can also look at a residual plot. This is a scatter plot of the residuals against the explanatory variable. So the x values are still going to stay the same, but instead of plotting the y values, we're now going to plot them against the residual. So how far is our predicted away from our observed value? Residual plots help us assess how well a regression line fits. So here is our original data. This is the NEA activity versus fat gain. We can see our least squares regression line and the points around it. Now, if we find each of these points residuals and we replot them, we can see how close this point is to the line. That's why its residual is that close to the line as well. To have a good residual plot, you want it to have a nice scatter around the line. You don't want to see any kind of pattern. So let's check our understanding. Find the residual for a subject whose increase in NEA by 620 calories and show your work. So remember to do this. The first thing you're going to have to do is plug in that 620. So if we find our predicted weight gain for the student who had NEA change of 620, we see that we predict that they will gain 1.37 kilograms. To find the residual, we're going to do the observed minus the predicted. Now, if we come up to our table and we find the student who had an NEA change of 620, we see that their observed weight gain is 2.3 kilograms. We predicted that it would be 1.37 kilograms, and that's going to give us a residual of 0.93 kilograms. This residual is positive because the data point actually lies above the line. Interpret the value of the subject's residual in context. The residual says that the person gained 0.93 kilograms more than what we would have predicted using the least square as a model. For each subject, did the regression line overpredict fat gain? For which one did they overpredict fat gain by the most, and justify your answer? So to do this, we would have to find each person of the 16 individuals, their predicted, and then we would have to find their residual. So if we set this up, and on these lines here, these are our NEA change for our 16 individuals. And we know what their fat gain was, okay? This is the observed fat gain for those 16 people. So the next thing we would have to do is we would plug all of these into our equation to find their predicted fat gains. Now to find their residuals, remember you do the observed minus the predicted. So you would do their fat gain minus the predicted fat gain, and you would get all of their residuals. Now we are looking for which one was over-predicted the most. If they are over-predicted, that means the line is above the data point. So if we look at our table, the subject who had an NEA fat gain of 500, NEA change of 580, has the smallest residual. That means the farthest to the negative. Because remember, if it's negative, that means that the line is above where the actual observed data point was. So we predicted that they would gain 1.51 kilograms, but the observed person actually only gained 0.4, which left us with a residual of 1.11 kilograms, which is largest residual below the line.